on Monday unless the students decide they don't want to lecture. That's when I was actually going to close the reinforcement learning series. On Wednesday we have a guest lecture, and I will require everybody to be present on Wednesday because it's humiliating to have a guest lecturer speak to an empty classroom, right? So anyway, continuing with the topic at hand, we have a lot to cover. And just to remind you, this is where we were, right? When we began talking about reinforcement learning, you were slightly above 0. You knew a little more than you do right now. And now the thing's going to fall off the steep, it gets fairly complex fairly quickly. And yet at the end of the day, all of the ideas are really very simple. So it's the magic of this whole thing. I mean, I don't think there was anything particularly complex that we have seen so far, right? So here's where we began. We spoke of Markov processes. So Markov process, come on up front. Yeah. So Markov processes are processes where the process is going to evolve to depends only on where it currently is and not on how it got to wherever it got to. Then we spoke of something called an information state, which allowed us to redefine the state of a process such that pretty much anything that depends on a finite amount of history can be expressed as a Markov process. And so we defined our entire environment and our world as Markov with an appropriately defined information state. We spoke of Markov reward processes. A Markov reward processes is one processes where wandering through the state randomly will occasionally give you a reward. Some states will give you rewards or even punishments. And so we had this fly Markov process where you had the spider trying to catch the fly, and we saw that we had to define the states properly. Here, for example, the state is the distance of the spider from the fly. And when you define it like so, then in this particular case, the only situation where the reward was obtained was when the fly got to state as 0. At all other states, the reward was 0. We defined the discounted return of a process, which is the immediate reward. Come on up front, sit in the front, right? So the discounted return was the immediate, the sum of all the rewards from the current instant into the future, except that the immediate reward was the only one that got the full weight, and then as you kept stepping further into the future, the rewards got discounted by this exponential term, gamma raised to k. Now, we introduced Markov decision processes, which was the same as a Markov reward process with one minor change, that the Markov decision process, in the case of the Markov decision process, the agent had agency in the sense that the agent chose their actions. The environment responded to the actions. In this case, the agent chose whether they were going to the spider being the agent, chose whether she was going to head towards the fly or away from the fly. And the environment, which was the fly, decided how it was going to change, in what manner it was going to change once the agent took an action. So now the transitions, as we saw in this particular example, were dependent on the action of the agent, but the transitions are a property of the environment. The actions are a property of the agent, but the agent's actions trigger changes in the behavior of the environment. It means the transition probabilities of the environment depend on the actions of the agent. So we saw all of these, right? We introduced something called a policy, which is the agent's choice of action in each state, where in any state the agent must act in a manner that maximizes the return, not the immediate reward necessarily, but the return, what the agent expects to get from here on all the way out into the future, right? And the policy, well, not every policy is going to be good, but you can have policies which are actually bad. The policy is not dependent on the outcome. The policy is just the agent's choice of behavior in each state. Some of these are good and some of these are bad, right? It could be stochastic. And we saw the Bellman expectation equations. This is all a quick recap, right? We saw the Bellman expectation equations where the expectation equation for any state, so the term within the parenthesis was the expected expected value of a state when the agent took an action A, and then the first equation, and the outer summation is basically summing over all possible actions that the agent could take under a particular policy. So the value for a state depended on the policy. The second equation that we are saying is exactly the same as the first one, except now we are not defining it merely for state, we are defining it for the combination of state and action, the state action value. All of this is old hat, we've been through this already, right? And then we defined something called an optimal policy. An optimal policy is a policy that maximizes the expected total discounted reward at every state. And we had an optimal theorem that said that for any Markov decision process there was an optimal policy. There's always an optimal policy that's better than or equal to every other policy. What we meant by that is that this expected value of every state was going to be at least as good as the expected value of every other state, right? And the optimal value function, so and then we defined something called a greedy policy. So the optimal value function gave you the highest possible value for every state, and an optimal policy is going to be is actually quite greedy. It's very simple. It's going to choose the action that maximizes the expected value for the state. So all of this we've seen, which led us to the Bellman optimality equations, which were not linear equations, which you couldn't just solve, where we said the value for any state under the optimal policy was the expected value, chose the action, was the maximum overall possible actions of the reward associated with the action plus the expected future value, discounted future value under that action, right? And we have the corresponding equation for state action values. Now all of this is a quick recap. We are not actually going to, this is just to remind you, so I'm not going to spend time on this. We're going to move on from this very quickly. And then we spoke of planning with an MDP. Planning with an MDP was where you were given the entire Markov decision process, every component of the Markov decision process. And you had to come up with the optimal policy. And there were two solutions. One was value-based solutions, where you found for any given, you basically found the optimal values for all of the states and then derived the policy from it. And then you had the policy-based solution where you directly found the policy, optimal policy for the process, right? Now again, going back, all of this hinges on these two equations, the Bellman optimality equations. If you understand these equations, everything else just falls into place. So again, value-based planning, we had this two-step process where we first, given a policy, we could predict the values of all of the states. And then there was a control where, being able to make such predictions, we now found the best policy. For the prediction, we used a dynamic program. We just iterated this particular value update equation continuously. And so we had something called a policy iteration to find the optimal policies. Now, I'm going through a lot of this, and it's amazing how much we have covered, but I think the coverage was sufficiently sequential and simple that pretty much every step made sense, given everything in the past. But when I present it all at once, it seems a bit overwhelming. So it's a lot of stuff, but it's actually very simple. Now, the policy iteration we saw was that you would begin with any policy, then you'd use the prediction DP to compute the values for all of the states. And then once you've computed the values for all of the states, you would update your policy using a greedy strategy. And then using the new policy, you'd go back and use your prediction DP to compute values for all of the states and keep flipping back and forth till it converged. We also saw the value iteration, where instead of trying to come up with a policy, you directly found the optimal value for every state. Now, the value iteration was only defined for you in terms of the value function, but I said you can do the same thing with the state action values. And I haven't given you the update rules for the state action values because obviously when I don't give you something, it means it's going to turn up in the quiz. So, and twice, right, just to make sure that you get that, and you get the answer. So all of this we saw we could do if we are given the details of the MDP. If I tell you what the states are, if I tell you what the actions are, if I tell you how the system transitions from one state to the other for any given action, if I tell you what the discount is, everything is given. I can go ahead, I can plan, I can control, I can find the optimal policy for the process. In real life, you're playing a game of chess, nobody's telling you what the actual underlying MDP is. In this case, what do? We no longer have a model for the world. And when you don't have a model for the world, you end up with this situation. It's called model-free reinforcement learning. When we had the model, we called it planning. If I don't know what the world looks like, I'm going to call it reinforcement learning. Now, these are not two disconnected subjects. The reason we spent such a long time talking about the whole business of planning is that we've set ourselves up so that now we can just use all of the ideas that we're familiar with and quickly go through the process of reinforcement learning. So what are the questions here? How do you find the value of a policy? Again, we're still going to assume that the system that the environment has states, that we know what the states are, that there are actions that can be taken in every state, and we know what the actions are. What we don't know is how the environment is going to respond. So given this is what because in any given situation, you have, at least locally, you have a pretty good idea of the states. You have a pretty good idea of what actions you can take. What you really do not know is how the environment is going to respond, right? So in this case, the question is, how do you find the value of a policy without knowing the underlying Markov decision process? If I cannot find the value, how do I go ahead and find the optimal policy? Once again, without knowing the underlying Markov decision process. So these are the two questions we're going to look at. So again, the assumption is that we can identify the states, we know the actions, we can measure the rewards, we just don't know anything about the underlying environment itself. We don't know the world. Under this condition, how are we going to find the values of states and the optimal policy? This is what we are calling the model-free assumption. Over here, for example, you're a spider. You must catch the fly, but you have no idea how the fly is going to respond. All you have control over is what actions you can take at each corner. And the actions are, I can go closer to the fly or I can go farther to the fly. So so here's the first thing we're going to do. How do you find the value of a policy? Suppose I decide on a policy. How do I find the value of the policy without knowing the underlying MDP? This is what I will call model-free prediction. So back in this fly metaphor, fly analogy, the spider decides I'm always going to try to get closer to the fly. So the spider knows its policy. What it doesn't know is how good is it to be three steps from the fly. How useful is it to be 2 steps from the fly? What is the value of being 1 step from the fly, right? These the spider does not know. Now, if the spider knew all of the parameters of the model, it could just sit down instead of, it could pull out a piece of paper and a pencil and figure out exactly what the value of each state was. But although the spider does have the paper and the pencil in this case, it doesn't know how the fly is going to respond, so it doesn't know what the value of the states are, but it knows its policy, right? So you're trying to find the value of the states given the policy. And there are the various methods we can use. The moment I say Monte Carlo, you basically, even if I just walk away from the class, I think you guys can sit down, close your eyes, try to figure out what the heck I'm talking about, and probably come up with the right answer, right? The interesting bits are the TD, TD1, TD2, TDK, and TD lambda, which we will look at. So what is the Monte Carlo method? The spider has to figure out what the value of every corner is, right? So it's in this room, right? The spider's here, the fly's somewhere. What is the value of being at a distance d from the fly? How can the spider figure this out? Easy answer. The spider begins wandering. Every now and then it's going to catch the fly, at which point a new fly pops up, right? And so after the spider walks around for a bit, it has a fairly good idea of how the system is going to respond. From that, it can decide. It can take a good guess at what the value of each of the states is, right? So mathematically, what would happen? The system is in any, the agent is in, the system is in any state S. The agent takes an action A. It receives a reward R, and then the system changes to a new state, S prime, right? This is how the whole system progresses. The indices are, the time indices I'm following Sutton's indexing scheme, so things may be a bit off. But what happens when the system just randomly proceeds? The agent randomly investigates the system. The agent has a policy, right? So in this case, what the spider is going to do is it's going to go towards the fly. The fly will respond. Then it's going to go towards the fly again. The fly will respond. It's going to go towards the fly again. The fly will respond. It'll keep doing this, and every now and then it might just catch the fly, right? So basically what is happening is the system is in a state, the agent takes an action, moves towards the fly. It gets a reward, 0 or 1. Then the system changes, right? So you're going to get the sequence: state, action, reward, state, action, reward, state, action, reward. This is one complete sequence of exploration, right? And from this, now you can just count and get a good value for the guess what the values are for each state. So remember, the value function for any state is the expected return from that state, right? So it's going to be the return for the expected reward for that state plus gamma times the expected reward at the next instant plus gamma squared times the expected reward 2 instants from now, and so on. That is the expected return at any time, correct? So I can simply write the and the policy, of course, is so the value of any state is simply the expected return return at any from when you start from that state, and this is going to be dependent on the policy. Like the spider decides to go towards the fly. So to compute this, what I'm going to do is something very simple. I'm going to we're going to let the agent explore the system. It's just going to wander through the system many times. So if it's the spider is going to wander across the room till it catches the fly. That's an episode. Then it starts again. It's going to wander through the room, still following the same policy. It catches a fly. Eventually, sometimes in 3 steps, sometimes in 3,000 steps, right? And then that's episode 2. Then it starts the process all over again. Different episodes might be different lengths. Within each episode, you have the sequence: state, action, reward, state, action, reward, state, action, reward, right? And now, let's consider this. Within any episode, you can compute the empirical return at each time. We've already seen how we can compute the empirical return at each time, right? We did this 2 classes ago. So for example, in the first episode, the empirical return at time 1 is going to be R12 plus gamma times R13 plus gamma squared times R14, and so on, all the way to the end, correct? So also the return at time 2 is going to be R13 plus gamma times R14 plus gamma squared times R15 and so on, right? You can just literally, if you once the spider has gone through this episode and caught the fly, and if it's kept track of everything using its little pen and paper, then it can say what was the return at each time. It can actually compute this, right? And so you can compute the return at every time through the episode. This is done. Now, what is my guess for the value of being in state 1? I can just go through this episode, find all the times at which I was at state 1, and take the average of the returns at those times. And that is my guess for the value of that state. Make sense? Right? It's very simple. We're not doing anything complex. Everything we're going to be doing is built off this really trivial idea. Okay? And so I can do this for each one of the states. Very simple. And now I'm not just going to do this for one state, I'm going to do this for all of my states. So here is how I would actually estimate the value for a state. I'm going to average this across many episodes. I'm going to do this over many episodes, right? Over each episode, in the first pass, I'm going to compute the return, the discounted return at every time. Then I'm going to go through this episode, and any time I'm going to have an incremental counter for the total return from that state, right? And anytime I encounter a particular state, I'm going to increment the number of times I visited that state. So I'm going to maintain a counter n of s for every state. And then as I go through the episode, as I'm analyzing the episode, I say, okay, I visited state s over here, so I'm going to increment the counter for state s. So ns becomes ns plus 1, right? And the returns I got from that state, I'm going to add the current return to it. Once I've done this over all the episodes, then I can look at the total return that I got for each state divided by the number of times I visited that state, and that's going to be my average return from that state, and that's going to be my guess for what the value of that state is. Again, nothing particularly complex, just straight up arithmetic, right? It turns out this arithmetic is really important. So I can actually do this online. I don't have to analyze all of the episodes. After each episode, I can just go back, analyze the episode, update my values for all the states, and then go on and perform the next episode, where one episode is one run through the system, like it would be the spider going over the room once until it catches the fly, right? So this is called Monte Carlo estimation. You're learning from experience directly. What you're doing is you're going through many episodes, and episodes where you're actually wandering through the system using your current policy. Remember, the value you're computing is for the current policy. So if you're the spider, you're just saying, what is the value of always going towards the fly? And you're going to keep following the policy all the time. And you're going to have many episodes. And then over each of the episodes, you're going to do all of this counting. And if you have a sufficiently large number of episodes, eventually the estimate that you get for the value of each state is going to be fairly close to that true estimate for that, to a true value for that system, for that policy, right? This is just for the value of a state, but you can do the same thing for action value pairs. How would I do this for action value pairs? Instead of just doing V of s, I can do Q of SA, where it's the same thing. I'm going to go through the episodes using my policy, right? And then at each state, I'm going to have an action. So I'd be computing is for the SA. And it's the same scheme. In each episode, I'm going to see how many times did this SA combination happen. And the corresponding average return is going to be the value for that state action pair. Same logic, nothing really changed, correct? So, questions? No. And I can do the same thing online. So, that's very simple, right? Even if I don't give you the system, if you have a policy, all you have to do is to wander through the process many, many, many times. And you can go back and you can compute the value for every state. Right? It's beautiful. It's very simple. And you can do this not only for every state, you can do this for every state action value, state action pair. So we've shown that you don't really need to know the underlying MDP. You can do this by exploring the system. It's basically like, getting training data to estimate the underlying process and then computing the actions and action values. Now, so everybody understand the notion of Monte Carlo, yeah?
Why bother computing the state and action pair instead of just computing the value associated with that state?
We'll see that towards the end of the class, right? We need this because when you want to compute the optimal policy, you're going to pick the action for which the state action value is maximum.
But like for value iteration, don't you just need the state value to compute the policy?
What else do you need? If I have the state value, I need to compute the state action value from it. For that, you need the transition probability matrix. We don't have the transition probability matrix, right? So you're right. If, in principle, if I know the system, I don't need to compute the Q's at all. It's sufficient for me to compute the V's. In practice, I don't have the transition probabilities. So I'm going to work off the Q's. Although there are many more Q values than there are V values, right? But we'll get to that towards the end. Okay. So now we understand the Monte Carlo method, right? But now, here is the problem with the Monte Carlo method. I'm going to have to run these episodes. I'm going to have to run many of these episodes. And each episode can be arbitrarily long, right? So, which means that there's no strictly online process. As I'm going through a episode, if I visit a state S, I have no way of updating my value for that state, because to update the value for that state, I need to know the return at that state. And the return depends on everything that happens in the future, right? Because the return is the sum of the current reward plus all future rewards. So until you get to the end, you cannot go back and update the value for a state. You don't really have an online process for this guy, right? What you would like to do is to say, as soon as I visit a state, I want to update the value for the state. And this mechanism, as we saw at the Monte Carlo, doesn't allow you to do it. We're going to make a small twist. And here is a very simple trick. We've seen a few high school tricks in this in the past couple of lectures. Here's one more. Suppose I have a series of numbers, x1, x2, x3, okay? I want to compute the average of all of these guys. The average of all of these guys is going to be 1 over n summation xi if I have n of these guys, correct? But suppose I want to do a running estimate and I want to keep updating my estimate. Then I can say mu1 equals x1. So as soon as I visit my first x1, I just give it my, say mu1 is my x1, right? Then my online estimate mu2 is going to be x1 plus x2 over 2. Because I keep updating my mean as I go through the sequence, right? Mu3 is going to be x1 plus x2 plus x3 over 3, right? I can keep updating myself as I go forward. But then look at what this is. Mu3 is simply 2 times mu2 plus x3 over 3. Why is that? Because mu2 is x1 plus x2 times 2. I can move this up here, right? So I can say mu3 is mu2 times mu2 plus x3 over 3. Or in general, if you work it out, you're going to get mu k is going to be k minus 1 times mu k plus xk over k. Yeah. So basically, after seeing k minus 1 events, k minus 1 x's, you have a current estimate for the mean. Okay, because this should be mu k minus 1, sorry. You're correct. Okay, so I can write that, yeah? So, or I can, now here is the really pretty bit. I can rearrange these guys and I can say mu k is mu k minus 1 plus 1 over k times xk minus mu k minus 1. Now what is the really cute bit that happened? I have a current estimate for the mean. If I see a new x, all I do is adjust my mean by the difference between the current value of the mean and the new x, scaled by 1 over k, right? Which means that anytime I see some new value, it differs from what I've currently got, I'm going to adjust what I've got. But if I've seen a lot of guys already, the adjustment is going to be small. If I've seen only a few guys, the adjustment is going to be large, right? It works really, really nicely, as you can see, right? But then I can generalize that to say mu k equals mu k minus 1 plus alpha times xk minus mu k minus 1, right? So if I write this, now how well does this update rule work, this online update rule? I can change the alpha. So here's a little simulation that I just ran on a bunch of numbers, and so the x-axis is how many terms I'm averaging over, right? The y-axis is the current estimate of mean, the mean. Akash, you need coffee or do you need to go wash your face? Okay, all right. So as you can see, if I use the correct formula, which is the one on top, mu k equals mu k minus 1 plus 1 over k xk minus mu k minus 1, you get the blue curve. Within a few steps, you get to pretty close to the actual value of mu. But then there's a lot of oscillation in the beginning and it sort of tapers off, right? But if I use an alpha which is not 1 over k, it still is going to sort of slowly converge to the correct value of mu. But it's going to converge in a smoother way. It's not going to oscillate around wildly, right? And so what we see here is basically that the correct equation, which is the blue one, is unbiased and converges to the true value. But even if I use any other alpha which is not equal to 1 over k, it's eventually going to converge to the true value, only much more slowly, right? And the smaller the value of alpha is, the slower it's going to converge. In the beginning, it's going to be fairly biased. The estimate is going to be biased, but afterwards it's going to be unbiased. Now, another thing you might observe is that you really want the alpha to fall off, to decrease with time, right? If it's constant, you're going to keep bouncing around, okay? So here's what we're going to do. Our action value, this was what the estimated value for every state was when we were running the Monte Carlo, right? First we ran the episode, then we went through the episode and computed the empirical return, discounted return at every time. Then you counted the number of times each state happened, computed the total return at every state. The ratio of the two gave you the expected value for each state, right? We've done this. Now GTI is the discounted return for the state at the time of the instant of the ith visit to the state. So I can rewrite it like so, right? I can use the incremental update rule. If I use the incremental update rule, it means that as soon as I visit a state, I can update my value for the state, right? What can I? Can I really update the value for every state over here as soon as I visit the state? Or is there still some dependence on the future? So is there a dependence on the future here? Because GT needs the future, right? To compute GT, GT is the return. You've got to see everything all the way to the end. So simply because I rewrote the update equation hasn't helped me one small bit, because this guy is a problem. It needs the returns, it needs everything all the way into the future. But now I'm going to play one more small trick. the gain, the return at any time is simply going to be the reward at that time plus the discounted return at the next time, right? So I can write it like so. If you don't believe me, look at it this way. So G1 is R2 plus gamma R3 plus gamma squared R4 and so on. G2 is R2 R3 plus gamma R2 R4 plus gamma squared R5 and so on, right? So in general I can write G1 equals R2 plus gamma G2, right? I can also write G1 equals R1 plus gamma R2 plus gamma squared G3. Or in general, I can write GT is RT plus 1. Again, there's a little indexing. Indexing is somewhat odd, but staying with it, right? So I can say GT equals RT plus 1 plus I equals 1 to n gamma raised to I, RT plus I plus n. Basically, I'm just doing this. I'm going to be summing rewards till some distance into the future, and then beyond that I'm just going to sum the return, right? The equations are still correct, nothing has changed, the equation is still right. But then here's what I will do. Instead of using, when I finally write the future return, instead of using the future return, I will write the future expected return at that state, at whatever state I was at that time, right? So if you look at what's happening over here, I can say GT is RT plus 1 plus gamma times the value of the state that I was in at time t plus 1. It's not the true return at that, true observed return at that state, it's the expected return at that state, right? Now this is a chicken and egg problem, because what I was trying to do was to estimate the values of the states in the first place. And if I'm writing the values in terms of the values, I haven't really helped myself, but you know what? I have a current estimate for the value, I'll just plug it in. And so I can just do that, right? It's called bootstrapping it by the current estimate. So this is what we will call the TD1, right? Temporal difference 1 solution, which is like so. I'm going to replace the GT in that update rule by RT plus 1 plus gamma times the value of the state at time t plus 1. Right? Very simple. Which gives me this update rule, which is going to be, and here is the pretty bit. All it says is that I'm going to take the current reward plus the difference between the discounted value of the state of the value of the next state minus the value of the current state. That's gamma VST plus 1 minus VST, right? And that's all I'm going to do. And this I'm going to add in, right? So this is my true online update rule. So here is the bit, right? Now here what I did was I modified the process by using, although I used the online update rule, but the online update rule required me to have the return for every state. The return needed the infinite future. But instead of using the infinite future reward, it needed rewards into the infinite future. But instead of using the rewards into the infinite future, I would just take rewards to one step more, and from there I just take the expected reward. Now this means, because I always have a current estimate for the expected value of every state, at any time, as soon as I visit a state and one more state, I can already update the value for the current state, and I can keep doing this. Now this is truly online. I don't have to wait for the game to end, for the episode to end, to go back and decide, update the value of the state. And here is a really cool bit. Now in an infinite horizons process, there's no such thing as a termination of an episode, right? So consider this thing. If the fly keeps jumping around, and the fly strategy is such that the spider can never catch the fly, right? If the spider is waiting to complete an episode to assign values to a state, it's never going to be able to do so, right? But using this process, you can say, oh, I think all states have 0 value. Takes a step, couldn't catch the fly. I still think all states have 0 value. Takes another step, couldn't catch the fly. I still think all states have 0 value. It's going to keep updating on the fly, as it updates, right? So it actually allows the system, even an infinite horizon system, to estimate the values of all the states without actually requiring for any episode to terminate. So here's the true online update rule. You have something like this. This is, you're going to go through many episodes, but within each episode, you're just going to be updating the values of every state as soon as you visit the state. It's not as soon as you visit the state. There's a one state look ahead, right? So as soon as you visit a state, you're going to update the value of the state just before, because you need VST plus 1, which means you need to know which state you arrived at, right? As soon as you take an action, you go to some new state, you're going to update the value for the state from which you took the action. So it's very simple. So this is our so-called TD1 update rule. It updates continuously. It improves estimates as soon as you observe a state, and can work with even infinitely long processes that never terminate. It's guaranteed to converge to the true value eventually, although the initial values will be biased, as we saw. Now here is the interesting thing. The TD estimates, the temporal difference estimates, can give you the correct value for any state, even when simple Monte Carlo estimates cannot. So here's a little example from Sutton's book. The figure is the real process that the real process. So during any episode, you're going to start at state A. You receive reward 0. You're going to either start at state A or state B. You receive reward 0 if you're in state A and go to state B. If you're in state B, 75% of the time you get a reward of 1, and then the game terminates. If you're off 25% of the time, you get a reward of 0, and then the game terminates. So what is the value of state B here? .75. What is the value of state A? There is no, the discount factor is 1. The value of state A is also 0.75, right? So now let's say you go through a bunch of episodes, and the episodes are written on the top left corner, right? And after having gone through these episodes, you just do a Monte Carlo estimate. What is the value you're assigning for state B? You visited state B 8 times. 6 times you got a 1, twice you got a 0, so you're assigning a value of 0.75 for state B, right? What is the value you're assigning for state A? 0, right? Because in the one episode where you actually visited state A, the total reward was 0. So that estimate is wrong, correct? But then let's try doing the TD1 process. If I'm using TD1, then I can keep revisiting states, okay? So if let's say I keep looping around, then I have VA, VB, they're both initialized to 0, okay? After the first step, what is the value that I'm going to assign to step 0 to first step of the first episode? What is the value I'm going to assign to state A? It's still 0, right? Because VB is 0, it's the current reward plus the future reward, the value of the next state, right? So it's going to be 0, and this too is going to be 0. Okay. The next episode, what happens? How are you going to update the value of state A? You don't visit state A, so you're not going to update the value of state A in the next episode, right? What is the updated value of state B? You visited state B twice. Half the time you got a reward of 1, the other half you didn't, right? So it's going to be 0 and 0.5. After the third episode, what will it be? What's the value of A? Akash? Uh-huh.
0.5.
After the third episode, right? Yeah. What is it? The third episode doesn't really have, you never visit A. So you never really updated A, right? What is what is the updated value of B? You're using the running estimate. So it's going to be 2 over 3. Right? 2 over 3. What about after the fourth? It's still going to be 0 for A, but for B it's going to be 3/4, right? What about after the eighth? Zero and 6/8, because look at what happened over there, right? Because the last one, B got a reward of 0, right? So it's going to be 0 and 6/8. We still don't have the correct value for A, right? But now I go back and loop over the eight episodes a second time. So the second time what happens now? What happens after the episode 1? What is the updated value for VA? You do visit VA, right? It's going to be the reward plus the return of the next state, because the discount factor is 1, right? What is it going to be? 6/8, 3/4, right? 0.75. Unfortunately, this guy changes. It's going to be 6/9, correct? But then by the time you get over here, you're going to get 0.75 and 0.75, right? And if you keep looping over it a sufficient number of times, eventually you're going to get the correct answer. So you see how the online update rule actually lets you get a correct answer, when the Monte Carlo method doesn't really give you the correct answer. So these online updates can actually be better than the Monte Carlo methods. Make sense? I see raised eyebrows. Wait, where did I miss you?
So why you can loop over the data until it converges?
I can keep looping over the data, right? There's nothing stopping over. And if I looped over the data the 100 times, eventually VA is going to converge to 0.75 and stay there. VB is going to be jittering around 0.75.
Will it blow up? Or
It won't blow up. Why would it blow up? Right? Think about this, right? So what happens over here? For the next 7 episodes, a VA is not going to be updated. So this is still going to be 0.75. This is going to be 12 over 16, right? Then I go back over here, VA remains 0.75. This is going to be 12 over 17, which is approximately the same as 12 over 16. So that VB is going to will jitter a little bit around 0.75, because both numerator and denominator keep getting incremented, right? Make sense? Sure. Okay. So basically it's going to converge to the correct value if I keep looping over the data, right? So the online really works. Now here is the key piece. We're going to step up and say, why do I have to stop with a one step online look ahead? I can look ahead twice, right? Because when I've taken one step look ahead, I'm going for the next state, I'm assigning the expected value of that state, but the expected value of the state is not precise. I'm still estimating these guys. So that's kind of noisy, right? If I took a two-step look ahead, I'm incorporating more information because I'm pushing the place where I'm putting the guess further out, right? As I keep taking more and more look ahead, I'm pushing the place stuff further and further out. So I can actually have a two-step look ahead, which is going to be RT plus 1 plus gamma RT plus 2 plus gamma squared, the value of the state 2 steps out. Or I can say RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3 plus gamma cubed, the value of the state 3 steps out. I can keep pushing my guess further and further out, right? And so when I push this out, if I push this out n steps, I'm going to call this TDN, right? And so the delta, remember we were saying it's a current reward plus gamma times the value of the next state minus the value of the current state, right? That is going to be changed by this delta n over here, which is the look ahead version of the future reward minus the value of the current state plus the current reward, right? That is the error that I'm going to be using to increment to update the value that I have for the current state in the formula. It's the same things that we've been seeing so far. And Anthony is fast asleep. Need to go wash your face? We're all right. We all right? Okay. It's the end of the semester, I know. Trust me, I'm more sleepy than you. I don't have the choice of sleeping while I'm talking. But so this clear to everybody, right? So look ahead is good, right? But then here is the problem. Can I really think of the current reward as the expected reward for the current state? I cannot, right? The reward is a sample. The more samples I add, the more variance I get. So the greater the look ahead, the more I'm grounding things and I really observe I'm grounding the estimate based on things I really observed, but also the more the variance, which means what I mean by more variance is that across different runs I'm going to see that vary more and more, correct? And so you have this classic trade-off that for a short look ahead, I'm working off estimates which are relatively stable, so the variance will be low, but I'm using less of what I really observed. Over a distant look ahead, I'm using a lot more of stuff that I observed, but they tend to vary more, right? Because the stuff that I'm keeping stable, which is the current estimate, although it's stable, it may be wrong. So I want to have a trade-off between using the right things, but not having things swing too much, right? So which means that if I want to pick, if I really don't like things swinging around wildly, I'm just going to use a one-step look ahead. But I'm unlikely to be very, very trusting of this one-step look ahead. And so I have to somehow figure out how do I both deal with a one-step look ahead and a one-step, deal with trusting what I see and not having things swing around too much. Why choose, right? So what we will do is we will use all look aheads. I'm going to get an estimate from the one-step look ahead. I'm going to get another estimate from the two-step look ahead. I'm going to get another estimate from the three-step look ahead, yet another from the four-step look ahead. Take an average of the lot, right? But then remember, the look ahead can be infinite, right? So am I going to trust my one-step look ahead as much as I trust my two-step look ahead? No. The further the look ahead is, the more variation there is, the more uncertain it gets out in the future, right? So I'm going to use the same kind of discounting process. I'm going to give the maximum value to the one-step look ahead, a little less to this two-step look ahead. So the weight I will give is 1 minus gamma to the one-step. I'm going to do this. I'm going to discount and add. I'm going to use a 1 minus gamma for the one-step look ahead. It's 1 minus gamma times gamma to the two-step look ahead. 1 minus gamma times gamma squared to the three-step look ahead. Why about this particular sequence? If you sum all of these, if you sum all of the weights, it's 1 minus gamma times gamma plus, so if you sum all of the weights, you're going to get this guy, right? You're going to get 1 minus gamma, this is from the one-step look ahead, plus 1 minus gamma times gamma for the two-step look ahead, plus this is for the three-step look ahead, and so on, right? Which is going to be 1 minus gamma times 1 plus gamma squared. which is going to be 1 minus gamma over 1 minus gamma, which is 1. So all the weights sum to 1. I could have used any other weighting scheme. I just chose this because it's nice and convenient. Yeah.
Why are we using another discounting factor? I thought we
It's,
were the rewards, right? Or not the rewards, expected return.
yeah, no, the point is that I'm just going to use the same. This discounting is how much I'm going to be trusting the different look-aheads.
Isn't gamma already in that though? We already have gamma
Gamma is already factored into the.
for the expected reward.
Yeah, so remember, you're not actually looking at the infinite return at this point. You're estimating the return, right? So I can have, so the returns use a gamma.
Yeah.
How much I weight all of the future terms could potentially use a completely different gamma, right? Or I could use the same thing. Doesn't really matter, right? Yeah. So all I'm saying is, depending on what my look ahead is going to be, it's not gamma, it's lambda. Lambda, as you will see, I've written lambda over here, right? They're two different things, right? So basically, all I'm saying is how much am I going to be trusting the look ahead. So I should really have said lambda rather than gamma. But you get 1 minus lambda or 1 minus lambda, the weights become 1, right? So here's what we're really going to do. I'm going to say that the expected return at any time under the scheme, which I will call TD lambda, is going to be 1 minus lambda time. Is basically the weighted sum of the returns, estimated returns with different look aheads, all the way into the future, right? And this is what I'm going to plug into my value. So this is beautiful, right? So the actual update rule now becomes very nice and compact. The update, whenever I visit any state, I'm going to update the value for that state by taking the expected return, which is summed over all possible future look aheads, minus the current value for the state. I'm going to multiply by that by some alpha, which typically falls off with time, and add it to the current estimate, right? Make sense? Except now I have a problem, right? Suddenly it's no longer just look ahead. It's no longer just, I can no longer deal with, it's no longer online, because the look aheads are getting further and further and further out into the past, into the future, all the way to the infinite future, right? So in order to get a more robust estimate of my expected gain, what I did was ended up looking into the infinite future, and the whole business of using these approximations to be able to do things online sort of got turned on its head, and I lost the ability to do things online, right? A look ahead still kept things online. I just needed to look ahead 5 steps, meaning at each time I was updating things that happened 5 instances in the past or 2 instances in the past. But now I can't do anything till I get to the end. But then something magical happened the moment I begin considering infinity. Infinities are beautiful things, right? How are infinities beautiful things? Look at what's happening. If I'm trying to update the value of the state at st, the things I'm using are the reward that I got, the reward I got at time t plus 1, which I'm weighting with 1 minus lambda. I'm using the reward at time t plus 2, which I'm weighting with 1 minus lambda times lambda, right? Because that's being used in the 2-step look ahead. The reward I got at time at t plus 3 with 1 minus lambda times lambda squared, and so on, correct? But then but instead of saying I am going to be looking ahead into the future, here's a different way of thinking about it when I'm speaking of look ahead, right? I can think of it as walking forwards by looking backwards. So now when I'm doing a 1-step look ahead, it really means that as soon as I get to a state, I'm updating the value of the state over there, right? If I'm doing a 2-step look ahead, as I'm going backwards, I'm updating the value of the state 2 steps behind, right? If I'm doing a 3-step look ahead, I'm walking with my facing backwards and updating the value of the state 3 steps behind. If I'm doing this TD lambda, what am I really doing? I'm walking back, facing backwards, And at each time, as soon as I take a step, I'm updating all the states, every single state, all the way into the back, into the infinite past rather than peering into the infinite future, right? So by saying, so instead of, by just changing the direction in which you're facing, instead of walking forward while looking forward, if you're walking forward while looking backwards, what was not an online process suddenly became online again, right? As you move, you keep updating everything behind you. Now this is really beautiful. Let's go back and look at the very first thing that we did when we were talking about a game of chess, right? So look at what's happening. At any time t, how much are you updating things in the past? You're updating the immediate previous state by 1 minus lambda. You're updating, this reward is updating something that happened 2 steps in the past by 1 minus lambda times lambda, right? Something that happened k steps in the past is going to be updated by 1 minus lambda times lambda raised to k. As you go further and further in the past, the contribution of this current reward becomes less and less and less, right? Now if you go back to the very first lecture where we introduced the chess game, we said that when you win a game, you're going to attribute that victory to every step that led you to that victory, right? But as you go further and further in the past, you're going to attribute it less and less. That's exactly what this is doing, right? The moment you win a single game, you're going to assign values to all the states visited during the game. You're using exactly the scheme. So I've just spent 4 lectures giving you the math behind the colored diagram that we saw in the first lecture on reinforcement learning. Right, it's very pretty. The math kind of works out, right? So here's how we will actually do it implementationally. I'm going to define something called an eligibility trace for every state. The eligibility trace for every state is, when I look back, some states would have been visited multiple times, so I'm going to update them multiple times, right? So if you look at all the red states are the same state. So the current reward is going to be updating the red state 3 times. Once for when it occurred one time step ago, once for when it occurred 4 time steps ago, once for when it occurred 6 time steps ago, right? It's going to be updating it 3 times, right? So the total contribution of the current reward to the red state is going to be 1 minus gamma plus 1 minus lambda, and 1 minus lambda times lambda plus 1 minus lambda times lambda raised to 4 plus 1 minus lambda times lambda raised to 6, right? So that summation is what I will call the eligibility trace for the red state. I can just compute that summation a priori, right? So I have an eligibility trace for the red, black, and yellow states, which is the sum of the weights. And it turns out I can compute it very simply when I'm doing my going forward. So at each time step, I will retain a total weight for every state. At each time step, after moving up 1 step, I'm going to shrink the weight for every state by lambda, except for the state that I have actually visited, to which I will add 1. Because I'm in the state, right? So basically what we are saying is, as states go further in the past, the less I've visited them, the less the current step is going to contribute to it. But the moment I visit some state at some point, I'm going to say, okay, this kind of adds to it, right? So this is the total weight for all the states until the current time. And so if you actually look at how the entire update process goes, we are going to say at every step, as soon as you visit a state, I'm going to turn my way back and I'm going to update the values for all of the states in the past. And the way I will update the values for all of the states in the past is that I'm going to take the difference between the current state and the value of that state, and I'm going to multiply that difference by the total eligibility trace for that state, and that is the correction term, right? So basically this guy, this delta S, is going to be the difference between the value of the current reward, or the value of the current state, and the value of the state I'm trying to update, right? And the eligibility trace just keeps track of the total weight of all the instants at which I visited that state in the current during the run, the sum of all the various lambda terms. And that is going to multiply this difference, and I'm just going to be adding things in, right? Again, the math is not hard. You just have to go back and look carefully at the slides to see what's going on, but it's very straightforward.
So the S here is every state on
On the path, on the state, and every state on the path. Every state in the system, but some states will have never been visited. So their eligibility trace is going to be 0, right? And so we basically managed to affect infinite look ahead instead by performing infinite look behind, by walking with our face backwards, right? And now you allow us to, every reward updates the value of all the states leading to the reward. So this is, and in fact when lambda equals 1, this just becomes Monte Carlo Markov chain. I mean, this is just Monte Carlo, straight up Monte Carlo, right? So it's very beautiful. Now, story so far, just summarizing everything. But what have we done so far? What we have done so far is to decide how to assign values for states under a particular policy. What is the real problem? How do we find the optimal policy, right? Just using the values, you cannot find the optimal policy. Why so? Because, let me actually skip this. Look at this guy. The optimal policy is going to pick the action for which the state action value is maximum. The state action value for any state is going to be the expected reward at that state for that action times the expected reward over all future states. But for future states, you need the transition matrices. To take the expectation over future states, you need the transition matrix. And we started off by saying we don't have the transition matrix. That's why we're going through all of this Monte Carlo, correct? So just having the value is not sufficient. What we really want is the state action value, right? And as things go, we know that everything that we did, we can actually just do the same thing with state action values, can we not? So instead of just updating the values for the states, I can update the values for state actions. So the same procedure that we saw used can be used for updating values of state actions, state action pairs, which means now I can use that, and at each state I can find which action maximizes the value and pick that as my policy. Yeah.
As an alternative, can you estimate value function and your transition matrix?
You could do that. You absolutely could do that, right? So you could estimate the value function, but the problem is the transition matrix is action dependent. So you're going to be estimating action dependent transition matrices for very large, but it's totally acceptable to do that, right? And in fact, people do that. They estimate transition matrices and then run simulations to get other kinds of stuff, okay? So, but here is the problem, right? Let me skip a couple of slides. So if I'm looking at state action values, right? The state action value, this episode depends on the policy, right? I'm going to be running for a very long time using the current policy to compute the state action values for that policy. Then based on those state action values, I'm going to be updating my policy, and I'm going to be repeating the process, right? And this is what we will call, but if I just do this, will my policy change in the next iteration? No, because I've already decided what action I'm going to use in every state, which means I'm never actually ever going to see anything besides the state action pair that my current policy decides, right? If I'm saying that in this corner I'm always going to go left, then it doesn't matter how many times I run the process, I'm never going to see the combination this corner and going right, because my policy says, current policy says going left. So what we really want to do is, even if we have an optimal policy, what we think is a current optimal policy, you just can't be following that all the time. If you do, you never give yourself the chance of saying, you know, maybe this was actually a better thing to be doing, right? So what we will do is to actually have something called an epsilon greedy policy, where we say that when you update your policy, you're going to say for every state, I'm going to choose the action which resulted in the highest value with a probability 1 minus epsilon. But with a small probability epsilon, I'm also going to try the other actions. Right? It's an epsilon greedy policy. And this leads to a whole slew of other things that we're sort of running out of time over, but this is kind of beautiful, right? And so that allows you to compute this guy. And now, if I were just using an epsilon greedy policy, now this is what gives us this algorithm called SARSA. Where did the name SARSA come from? You have the state. At the state, you follow an action. You take an action. You receive a reward. Now the environment transitions you to another state. At that state, you take the next action, right? So you have SA, you get a reward, then you have an SA, and you're using the QSA for the next time to update the QSA for the current time, right? That's how we're actually doing the update rule. So you have SARSA. If you read it, it looks like it reads as SARSA. So that's a SARSA algorithm, or the greedy in the limit of. It's a GLIE is greedy in the limit with infinite exploration. That's the algorithm that we actually use. Okay. Now this action is all very fine, but here is the really interesting thing. See what is happening. When I'm looking at state action pairs, I'm at a state, I take an action, I get a reward. I arrive at another state, I take another action, right? So this update rule is looking at the state action at the next time, the value of the state action at the next time, the value of the current state action. It's taking the difference between the two to update the value of the current state action, right? But is it actually checking if you really took the action A prime the next time? It's not, right? I could have completely said, I could have picked any A prime, because you only have a one-step look ahead. There's no look ahead beyond the first step to decide if you actually took the action A prime. Does that make sense to you? Right? So here's what is happening. You would actually be doing something like this: state, action, reward, state, action, reward, state, action, reward, right? It's looking at this combination and this combination, looking at the difference between the two to update the value for this combination, right? But suppose you're looking ahead, and let's say at every state you've got a guy who says, oh, now the action is R, right? But the guy lies and tells you a completely different action than what was actually followed, right? So in that case, what would happen is that when you're updating this guy, you're going to be updating it based on this combination, whereas the process itself follows this combination. Does that make sense? The future action doesn't have to be what is really followed. So that leaves us with the very beautiful that leaves us with this very beautiful situation where you can do something called on-policy learning versus off-policy learning. So which means over here, I may have two different policies. One policy says you must take this action. I have another policy which says take this action, right? So if I use this guy to update this reward, this value, I'm actually learning about this policy. If I use this policy, I'm actually learning about this policy, right? So in other words, the action that I use at the next instant to update the state action value at the current time instant can be from a completely different policy than the action that I actually follow, right? And I'll actually stop over here because we're kind of running out of time, but this leads to all kinds of interesting, I won't spend more time on this. Maybe in the next class we'll go over some other details, but actually how we actually do this with neural networks and things like actor critics and so on. But now this leaves you with something really beautiful, right? Which is, suppose somebody just gave you a random sequence, SAR, 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 right? This is a real sequence of events that happened. This sequence of events doesn't have to do anything with the policy that you're currently evaluating. You can compute state action values for your policy, for any policy, using this sequence obtained using any other policy. How would you do that? So you're going to go over here. You saw SA, right? And then you go here and say, what if I chose this other policy that I'm trying to evaluate? And that other policy is going to choose a different action A prime, right? And then I can look at the difference between these two guys and update my state action values, and I'm going to be updating my state action values for this other policy, the one that asks me to go to A prime, which we will call off-policy learning. Now, if you think about it in terms of chess games, right, then if you're looking at somebody else playing a chess game, and that person is playing something completely different from what you yourself are playing, you can still use that to improve your own game, because at each point you'd say, I would have made that move, right? And based on the move that I would have made, I can improve my guess of the current state, right? So this is me playing. This is Magnus Carlsen's own idea of how I should have played. And Magnus Carlsen, it turns out, can learn from watching me play. Isn't that amazing? Right? So because at each position, he can look at every foolish situation I've actually set myself up into. Think of how he would have played it differently. And based on the difference, he can actually say, oh, this is what I could do even better. It's very interesting. I'll stop here because we're getting shoot out, but also I'm tired. But we'll pick this up, and maybe I'll try to wrap this up in the next class. This should have taken less time than it actually did. I might record a lecture on Friday if I can get a slot to complete my variational autoencoder lecture. Unfortunately, as it happens, we can't have a guaranteed slot for recording, so it may or may not happen. Thank you, guys.